Hi, and welcome to a new session of the Who is Who of Enzymes. As you can see, my topic is carboxylases and decarboxylases. So let's start with a quick overview. I will start first with a classification, then I will talk about carboxylases and decarboxylases which occur in nature. I will shortly talk about the role of carbon dioxide in large-scale chemical industry. We will talk a bit about subclassifications, mechanistic aspects, and at the end, I will give some selected examples in biocatalysis. So let's start with the classification. By definition, decarboxylases belong to the enzyme commission 4, which is the class of liases, which usually catalyze reactions that involve non-hydrolytic bond breaking, and these liases are usually called synthases. On the other hand, by definition, carboxylases belong to the group EC6, which are the ligases, which catalyze reactions that result in bond formation. However, with high energy cofactors, and this group is usually called synthetases. In fact, various enzymes which are able to catalyze either decarboxylation or carboxylation are loosely referred to as carboxylases or decarboxylases, which means that there is not really a strict differentiation. And so the difference between liases and ligases is usually based on their functions in the biological systems. So let's start with some examples from nature I would like to show you. First of all, this pyruvate decarboxylase, which is probably the most prominent example because it's important in alcohol fermentation and also in the glycolytic pathway. As you can see, the reaction which is catalyzed is the decarboxylation from pyruvate to acetaldehyde. And this is done by a TPP-dependent pyruvate decarboxylase, which means thiamine diphosphate dependent. And this acetaldehyde is formed, which is then reduced to ethanol by an alcohol dehydrogenase and NADH. Another example I would like to show you is this benzoyl formate decarboxylase, which occurs in the mandalate pathway. And as you can see, once mandalate is racemized, it's oxidized towards this benzoyl formate, which is then decarboxylated by this benzoyl formate decarboxylase, which is again TPP dependent. So to yield benzaldehyde, which is then oxidized towards benzoate, which can then be used as a sole carbon source for the beta-keto adipate pathway and also for the DCA cycle. And this pathway occurs usually in organisms like Pseudomonas botida, Pseudomonas aeruginosa, and also Acinetobacter calcoaceticus. The last example I would like to show you here is also an example I will mention later on during the presentation. It's it's more pyruvate decarboxylases which occur in this Ehrlich pathway, and this Ehrlich pathway is, as you might know, responsible for the catabolic degradation of amino acids. You can see an amino acid is oxidized via an amino acid aminotransferase towards this alpha keto acid. And this alpha keto acid is then decarboxylated by a pyruvate decarboxylase, which is again TPP dependent, towards this fusylaldehyde, which is then either reduced to this fusyl alcohol or oxidized to the fusyl carboxylic acid. And in general, so you just saw some examples for decarboxylation in nature. There are in general 4 major pathways for the fixation of CO2, which you can see here, which is first the Calvin-Benson cycle, then the reductive DCA cycle, the reductive acetyl-CoA cycle, and also acetyl-CoA pathways. And I just want to mention them. I won't talk about them now. Just to mention that the enzymes which occur in these cycles are so part of the primary metabolism, which means that these enzymes are usually show a quite narrow substrate scope, so they are not that feasible for biocatalytic applications. this leads me to thermodynamics. So in 2010, a review was published by Sylvia and Kurt, and they also published some quantum calculations where they investigated the carboxylation direction of different decarboxylases and carboxylases for different substrates. And as you can see, for most of the substrates, the carboxylation direction is strongly endergonic. If you have an aldehyde or an CH acidic acceptor and the enzyme is ATP dependent, also very endergonic. If you have an amine as well as an aromatic system. If you have here, for example, an activated aryl CH acceptor, for example, this phenyl phosphate, you have a thermoneutral reaction, and for a substrate which has this strain substrate like structure like this oxyrane, you have a strongly exergonic reaction. Shortly, I would like to talk about the role of CO2 in large-scale chemical industry. As you might know, it's very important for processes like the urea production, which is still performed in a scale which is just amazing, 95 megatons per year, but also for the methanol production, so the reaction of CO2 with hydrogen gas, and also the production of either cyclic or linear carbonate derivatives, and also the Kolbe-Schmidt synthesis, which leads to the product salicylic acid, which is then also used for the production of aspirin, for example. So these reactions are not, so except of the Kolbe-Schmidt synthesis you see here, are not like carboxylation reactions. They're rather like CO-CN coupling reactions. And for the carboxylation reactions, there has been a lot of progress made, as you can imagine, in transition metal chemistry, organocatalysis, and also electrocatalysis. I won't talk about these topics in this presentation. At the end, I will give some more references you could check out if you are interested. So I would like to talk again about the enzymes. And here you can see a subclassification of decarboxylases, which are not like the ones I showed you at the beginning, which derive from the primary metabolism, but from the secondary metabolism. And so from biodetoxification pathways, for example. And I want to talk a bit more about these because enzymes from the secondary metabolism usually have a much more relaxed substrate scope compared to the enzymes from primary metabolism. And these enzymes are usually used for decarboxylations or carboxylations of aromatic substrates. And we can subdivide this in 3 big groups, which are here the first group, which is the divalent metal-dependent decarboxylases which do not use cofactors at all. And on the other hand, the big group of this new cofactor, which is a prenulated flavomononucleotide. And so let's talk a bit about the mechanism. Here you can see just the generic carboxylation of a CH bond. First, the deprotonation is happening, which yields a carbanion, which usually has to be first stabilized so that it can nucleophilically attack this activated CO2 molecule. And so you get your carboxylated product. A bit more in detail for one of the classes I just mentioned, for the divalent metal-dependent decarboxylases, they're also called amide hydrolase superfamily. And usually you have a metal center, which is either zinc 2+ or a manganese 2+, and you have a substrate which looks somewhat like this. So the phenolate group and the carboxylate group chelate to the divalent metal center. And so by help of this aspartic acid residue, a protonation happens at this ipsocarbon of the carboxy group, which also leads to the dearomatization. And this decarboxylation is accompanied by rearomatization, which is also followed by the release of CO2 and the product molecule here. And in general, you have some requirements regarding the substrate for this mechanism. So you need phenolic OH, you need, of course, a carboxylation site in ortho position. Regarding the meta position, you're rather restricted. And for para, you have some possibilities of substitutions. Another class I showed before is the cofactor independent decarboxylases, which are acid-base catalyzed. And as you can see, you need a fully conjugated system. So you need a phenolic OH here, and also a carboxylation site at the beta carbon. And the mechanism goes that, so like this, it's first deprotonated, which leads to this quinone metide intermediate, which is followed by the reversible decarboxylation here. Another class I want to mention is this ATP-dependent paracarboxylases. So you have a phenol which has to be first activated. It's forming this phenyl phosphate, which is then hydrolyzed, and afterwards it attacks the CO2 molecule. But in general, these enzymes have also a quite narrow substrate scope. So there is an alternative actually, which is this very interesting group. It's this prenulated FMN dependent decarboxylases I mentioned before, which is also called UBD superfamily. And this prenulated flavomononucleotide as a cofactor was just discovered actually very recently in 2015. And here you can see how it is formed. So FMNH2 molecule reacts with DMAP, and the enzyme prenyltransferase UBX leads to this species, which is this prenulated FMN in the reduced species, which is then by oxidative maturation and the enzyme apodecarboxylase converted to the catalytically active species. And here, in this case, we have actually two species which can act as the catalytically active molecule, which is either the iminium ion or the azometine I lead. And it depends on the structure of the substrate molecule, which species is the catalyst. And if you have, for example, here, the conjugated unsaturated carboxylic acids, which are catalyzed by, for example, the enzyme FDC1, which is the ferulic acid decarboxylase, we have this azometine I lead as the catalytically active species. And so the mechanism starts with a 3+2 cycloaddition, which leads to this 5-membered pyrrolidine ring, which is then followed by a decarboxylation. And after protonation, we again get this pyrrolidine ring species, which is then finalized by this retro 3+2 cycloaddition, yielding this final alkene product. And the catalytically active species is restored. On the other hand, we have this iminium ion as the catalytically active species. And in this case, if we have substrates which look like these protocatechoic acids, we have first a nucleophilic attack by the start of the deprotonation of this lysine residue. And what we get is this quinoid cofactor intermediate, which is then decarboxylated and rearomatized. And by another protonation and dearomatization and rearomatization, we get to the final catechol product. And this class of enzyme is quite interesting because it has, also for biocatalytic applications, since we have a quite nice substrate scope. On the one hand, reactions, so this reversible decarboxylation of non-aromatic alpha-beta unsaturated acid derivatives is catalyzed, as you can see here, but also activated and non-activated aromatic substrates. So for example, this reversible decarboxylation of this 4-hydroxybenzoic acid, but also of catechols. We have the carboxylation of polycyclic non-activated hydrocarbons, which you can see here, and also the decarboxylation of toluene-CoAs and the carboxylation of phenyl phosphate. Moreover, we have also the reversible decarboxylation of heterocycles. For example, here the decarboxylation of pyrrole 2-carboxylic acid and also indole-free carboxylic acid. And here we have the decarboxylation of 6-hydroxyquinolinic acid, as well as the decarboxylation of this 2,5-furan decarboxylic acid. So in general, for biocatalytic applications, there have been performed two main strategies, which is on the one hand, the metabolic engineering for the production of a limited set of carboxylic acids. And so this is so with enzymes from mainly the primary metabolism, and on the other hand, which is more suitable, is the use of carboxylases, which occur in the secondary metabolism because they have a more relaxed substrate scope, and they also enable the retroselective carboxylation. Good. This leads me to just some examples from literature. I would like to show you this example, which is actually very old, but it's interesting because it's still performed in industrial scale. So this reaction was patented already in 1930. And so a pyruvate decarboxylase is used, which I showed you at the very beginning. And at the beginning, when it was patented, the substrates were used together with whole yeast cells. And so scientists did not really know what's going on. Just 60 years later, it was discovered that pyruvate decarboxylase is doing the job. And what I did not show you at the beginning is that this pyruvate decarboxylase is not just able to perform this decarboxylation of these pyruvate-like compounds, but is also able to form these acetyloene condensations with these different products here. So in this case, the product is L-phenyl acetylcarbinol, and this is then can be further used for the production of ephedrines and pseudoephedrines. One more example, because I said before that that the carboxylation reaction is usually not favored. So usually we have an uphill reaction, but so in 2001, this was one of the first publications where it was shown that it's doable to use the decarboxylases also for the carboxylation, which you can see here. And what they did was to engineer the conditions of the reaction, and they used different pHs and different concentrations of bicarbonate as the CO2 source, and they received a maximum yield of 81% at pH 11 and 500 millimolar bicarbonate. However, at that point, it was rather questionable if this procedure is applicable in an industry, since pH 11 is already like a harsh condition, and also high salt concentrations is not the best for industry. And this already leads me to the last example here I want to show you in biocatalytic applications. This was published just in 2018 in Nature Catalysis, and here they again show that decarboxylase, which is usually decarboxylating in a primary metabolism, which I showed you before from the Ehrlich pathway. So it was the reaction from alpha keto acid towards this fusylaldehyde. This can be also used to carboxylate in this case. So they used methional as a very cheap starting material. carboxylated it towards this M2AB intermediate, and then they coupled the whole system with a transaminase to produce this L-methionine, which is quite nice because nature is actually doing it much more complicated in much more steps. So it was a very nice proof of concept. And well, this leads me already to the conclusions. In general, I want to highlight some things. So many important decarboxylases and carboxylases occur in the primary metabolism, especially also in the CO2 fixation, but these enzymes are not that interesting for the biocatalytic applications since their substrate scope is rather narrow, and also protein engineering studies showed that the selectivity gets harmed. So if you change them, and enzymes from the secondary metabolism have a much more relaxed substrate scope, so they are more interesting actually for us. And as you saw, I just showed you some mechanistic aspects. In fact, this decarboxylases and carboxylases group are using a lot of different mechanisms. It's a very large spectrum. And in 2012, for example, it was published. So it was reported that there are so many different mechanisms of carboxylases and decarboxylases that you could subdivide this enzyme to classes. So in over 90 classes, so that you can just imagine it. And also, although the carboxylation direction is usually not favored, it's still possible to perform the carboxylation direction if you perform some engineering of the reaction conditions. With that, I'm already at the end. I would like to thank you for attention, and here you can see some more literature. If you're interested, you can just check them out. Thank you.